the name of this video is Electromotive Force. So, is it sufficient to have an electric field E to establish a steady current with current density vector J? The answer is no. Let's try to understand why this is the case. So, in order to have a steady current J, we know that J has to be a solenoidal field. A solenoidal field, like the word solenoid, we will encounter this again when studying inductance. It's a closed loop with many rounds, if you want. And so a solenoidal field means the field lines are closed. This is the opposite of an electric field, which is irrotational, so there is a source and the field lines spread away from this source. In this case, that's not the case. And as I said, the other field, which is also solenoidal to be encountered in this course, is the magnetic field B. So J is solenoidal. Since it's solenoidal, the field line has to be closed, which kind of makes sense qualitatively, because as I said before, a steady current can only be established not in vacuum, but in a conductor. So I need to have a closed conductor that is a circuit. For example, in the lab, we use wires made of copper with a certain gauge, let's say 24, like the one you can see in this video here, in this picture here. This is a typical wire, a very tiny wire with a uniform cross-section, which we use to establish a current. And it has to be a closed circuit. Circuits are closed. So intuitively also this makes sense. So let's consider a closed circuit. With a certain cross-section, I will come back to this in a few minutes. So this is a conductor, C. C, now on in these videos, we mean a conductor. So this conductor, again, is characterized by a certain cross-section, and let us say that it's characterized by a longitudinal axis as this one. Gamma, as always, which is a closed line solenoidal field. So now let's suppose that we want to establish, for example, the point here, we have a current with density J, this current here, which again is steady current, and we just hypothesize for a minute that the only field required to generate this, to establish this current, is an electric field like this one here, E. And again, the question is it sufficient? It is necessary, as I already mentioned in a previous video, but is it sufficient? That's really the question, sufficient or not. So we have this electric field E. Well, we know that for steady currents, the rotational property of the electric field, remember that now we don't call it static because we are in dynamics, but still is a steady current. So we know that the circulation along a closed line such as gamma of E dot TDL has to be equal to 0. This means that if I multiply this quantity times a charge, Q, which is the charge I'm attempting to move along this circuit, this is the charge free carriers in a conductor would be electrons, well, this means that the work associated with this quantity here, so W to move along the entire closed circuit, the Q, the charge Q, has to be equal to 0. So clearly, an electric field, which is conservative in steady conditions, generates 0 work for a charge which has to go on a closed loop, and the closed has to be closed, the loop, in order to have a steady current. So clearly, there is no work, and electric field is not sufficient to establish a current J. And why is that? Because E is conservative. In fact, as we know, in a simply connected domain, this property is equivalent to say that the field is conservative. It's rotational, therefore, in this case, conservative. All right. Let's try to understand a little bit more closely this concept. And so let us assume for a minute that our circuit here is a quasi-filiform circuit. You could also do it for a filiform, I prefer quasi-filiform. We encounter quasi-filiform flux tubes and so circuits in a previous video, So we have a quasi-filiform circuit with a cross-section here, delta A. In the filiform case, it would be dA, an infinitesimal quantity. And let us suppose that it is quasi-filiform uniformly along gamma, that is, this cross-section is the same everywhere. So if I pick another cross-section here, this is exactly the same delta A as this one. Okay, so same cross-section. So the cross-section is also very small. That is, all properties, if I pick this cross-section here, where Q is located, both J and E are effectively the same at each point of this cross-section because the cross-section is very small, quasi-filiform, and uniform. Note that this argument I'm about to do, you cannot do it if you don't assume a uniform cross-section. Remember the Euler and Lagrange perspective reference frames to understand this concept. In fact, you can discuss about this in Piazza. But okay, now let's consider this simple case, and let us suppose, in addition, that this conductor is a ohmic conductor. So we've seen Ohm's law in local form in one of the previous videos, so we know that in this case, before actually even entering so the Ohm's law, I will use it in this equation here. So let's already put here this with Ohm's law. Okay, but before doing that, we know that we have a solenoid that is a steady field J. What does it mean? This means that the surface, the flux to an equal surface of J has to be equal to 0. That's the fundamental property of steady current. Now, for a cross-section like this one with area delta A, and let's call this generic cross-section capital sigma, which again is the conceptual surface associated with an area delta A in this case, so it's this cross-section, I just call it capital sigma. It's an open cross-section, of course, so we know that the flux through this open surface, capital sigma, at any point P on this line gamma, as we know, so we know the property of J dot NDA, the flux of J, this effectively, now note that this N, effectively in this case, you can either call this N, this quantity here, so this is N, you can also call it T. It depends. If you're using a circulation, you go for T. If you're using a flux, you go for N, but in this case, N and T are actually, in many of these videos about to come, are the same concept. So don't make confusion with N and T, they're actually the same in this case. So this J.NDA, we know that I'm picking, if this is a quasi-filiform conductor here, effectively, gamma and J are the same field line. Okay, so it's a field line of this object. So this is a field line, therefore J has actually the direction of T, or N, if you want. So it's an amplitude, J, a magnitude, times direction T, if you really want, dotted with N, but T and N in this case are the same thing, dA. So this quantity clearly gives us, we are doing the integral over a very small quantity. It's so small that we can kind of forget about integral. So this result effectively is, since J is constant over our delta A, if you want, so it's nothing but J delta A. And this J delta A, we know that has to be equal to a constant, which is the current intensity associated with this cross-section capital sigma, which we know has to be a constant. This means that J has to be a constant because delta A obviously is a constant. It's the constant uniform cross-section across this flux cube in this case. Great, so now let us use Ohm's law because I'm also assuming that I have an ohmic conductor. So the resistivity associated with the conductor is Rc and its conductivity Sc. Therefore, we want E, which is going to be, so let's forget about this cube because it's equal to 0, so we can remove it. And so we're going to have E, Ohm's law, is equal R, if Rc is the resistivity of this conductor, okay, this is the resistivity, well, we can factor that out because assuming spot is a constant, so we have Rc, line integral along gamma, instead of E now I'm using Ohm's law, so it's Rcj dot TDL, but we know that J and T have the same direction because J is a field line of, gamma is a field line of J basically. So in this case, this results in R, C, J times the line integral, so this J dot T is a constant, which I can take outside the sign of integral here, and I end up having the integral of cosine gamma dl, which is nothing but the length L of this line, so assuming that this line is long L. So this means that RC different than 0, the length of the line is different than 0, times J has to be equal to 0, J has to be equal to 0. So clearly, having only an electric field is not sufficient to establish a current J, otherwise the current has to be equal to 0. So this also, again, corroborates our qualitative understanding that the work on a charge-free carrier is 0, which is actually a more general argument than this one. I only wanted to do it for a quasi-filiform, uniformly arranged wire, which is very common in real life, actually, and for an ohmic conductor, just to make it a little bit more clear, I hope. Good. So now we know all that. So what is the outcome of all this discussion? That E is not sufficient. So the answer here is absolutely not. No. So what do we do in order to establish a current J? Well, we need to introduce another force, which is like a hand which moves the charge-free carriers and allows the current to be established. And this force is generated by what? By a battery, a source, a generator. So let's call it a battery. B for battery. Great, so now we need a battery, okay? So this battery, let me just say that we are not going to discuss the microscopic behavior of this battery, which is chemical. So you have chemical, typically, if you take a battery, like a 3-volt battery, there is some chemistry happening. So if you look at the chemistry, obviously chemistry is the reaction of the electrons, the valence electrons. And so obviously, in the end, is electromagnetism. And so the microscopic phenomena happening inside the battery obviously are of electromagnetic origin. However, macroscopically, we interpret them as if they were a non-conservative force, opposite to this conservative field E, which is not sufficient to establish a current. So I need a battery, and the major outcome of this battery, the first feature of this battery, that generates a force, which we're going to call Fm, M for motive, which gives motion. Fm is the electromotive force. The electromotive force, which is non-conservative. So that's the first feature. Another feature that we really want to use, it has to be confined within a limited region of space. So it's confined within limited region. What is the limited region? The battery itself. Good. So these are the key elements of this. The electric field, which is conservative, on the other hand, can spread everywhere in space. It's not only confined within the battery, but it's everywhere. So the electric field E lives everywhere, including the battery. The field associated with Fm, which we call EM in a minute, is only located within the battery. So eventually, I need the superposition of the field associated with Fm and the field associated with E, which exists simultaneously within the battery, but outside the battery, only E exists. And now let's understand this a little bit more in detail. Okay, so let's make a sketch where we do have our battery here. So our battery looks like, let's say, this. So this is the top plate of the battery. I'm making much bigger than what I would like to, because I still want to use this filiform or quasi-filiform assumptions in all these arguments. So now we are assuming this everywhere, okay? And study currents everywhere, of course. So this is the top plate, which typically called plate 1. The bottom plate here, I call it plate 2. This is a confined region of space, which is our battery B. Good. So now, inside the battery, there is my hand, it's a microscopic hand, and what it does, it generates a field EM. Of course, EM is nothing but Fm, apparent definition of field, divided by Q, the charge free carrier moving. So there is this EM, which goes in this direction, from 2 to 1. And so what this does, it depletes charge-free carriers. Let's call it, in this case, by assumption, let's say that this field is moving positive charges up, and so I'm depleting positive charges from below, so I'm going to have negative charges below here. So depletion of positive charges, so negative effectively down there, whereas up here, I'm going to have an accumulation of positive charges in this fashion. That's why I call these plates 1 and 2. 1 is associated with the positively charged plate of the battery, and negative is, of course, 2. So when you take a battery, you know what it looks like. Look at this picture here. We have a plus and minus. These are the plus and minus of a battery. Good. All right. So now with that, clearly what happens is that this hand pushes these charges. So of course, as a reaction to that, as always, as we know, there will be also an electric field E, which goes between the plates of this battery in this direction. Typically, this field E is smaller than the field EM, otherwise you cannot have a current, and we will discuss this in detail in a few videos. Okay, so that's what's happening here. So the electric field E, if I look at it, inside the battery is like a parallel plate capacitor. We have seen the parallel plate capacitor, right? Plus, minus. Good. So that's the way the field looks like, and let's say it's uniform and simple because everything is small. Outside the battery, we didn't discuss in this course electrostatic dipoles or electric dipoles. We're going to see this more in detail in 342, but I can tell you that outside, I just said that the field E has to live everywhere in space, so outside, the field lines will look like that. So these, they close up, so they go from plus to minus, from plus to minus, and the same thing happens everywhere, also for these lines here. So these are the field lines of a dipole. So the electric field, which is conservative, lives everywhere, within and outside the battery, always from plus to minus. So outside it goes in this direction, inside in this direction. EM lives only within the battery, is confined, which is kind of critical for the non-conservative property we're about to write down. So that's what we have here. So we want a confined, check on that, non-conservative field. That is, if I were to compute, for example here, the circulation. Okay, so now here we want to do a circulation in order to unveil the fact that this electromotive force is actually a non-conservative force macroscopically. And so how to do that? For example, we can connect this battery to a quasi-filiform conductor, which corresponds with the longitudinal axis, corresponds with the field lines of the field E in this case. For example, like this, we could choose whatever you want, of course. I choose this for simplicity. And so that's our conductor. So this is our conductor C, this is our battery B. And so now we can choose a closed line along which to perform this circulation. And so this closed line will go in this direction here. So we go straight up here, then into this conductor in this fashion, and close like this. So it's oriented in this direction here and in this direction, in the same direction as EM. Okay, so this line gamma is given by the union of gamma in the conductor, which is this external part here. So from this point to this point is gamma in conductor, union gamma in the battery, which is this portion here. So this portion is a gamma battery, to make it absolutely crystal clear. Same direction as EM. So I want to perform the circulation along this gamma, which is a closed line of FM, or if you want EM, it's the same thing because we can get rid of. No, actually, let's keep it. Let's keep the Q now for generality. And so this circulation, actually, it's effectively equal to what? Well, we know that the M is confined within the battery, so we can say that this is Q times the line integral on gamma battery only of EM, because EM is 0 anywhere else, dot TDL, and this quantity we want absolutely different than 0, so it has to be non-conservative, as we already specified up here, okay, macroscopically non-conservative. Good, so now we have a macroscopically non-conservative quantity, field EM. So as it turns out, this quantity here, which I'm highlighting here in yellow, which is the non-different than 0 quantity, this quantity has the units of what? Of volt, obviously, has the same units of volts. So the SI units of this quantity is volt, and this quantity, we called it epsilon, or E, this funny E, this quantity which has the SI units of volts, volt, this is also called the electromotive force, or EMF. Now, this is the actual force, clearly it's a force. This one is a scalar, with units of volt, and yet people called it the electromotive force, EMF. So it's very confusing, but that's the way it is. They're both called electromotive force. Typically, we will never discuss about FM anymore in this course, maybe EM, which is the electromotive field. So in general, there is not really too much confusion because FM is never touched. So we will use specifically the term electromotive force, or EMF in brief, for the quantity scalar E, which has units of volts given by this integral, which has nothing to do with FM, of course, and electromotive field EM. So these are the quantities, so you can forget about that if you want. Why is it called the force? Complete historical reasons. I think Faraday and other people in the 19th century defined it like this. Bad definition, but it's still used today. So we want to use it just for consistency with the notation used by anybody else. All right, so this quantity has to be different than 0, so that's our non-conservative quantity. The beautiful thing of this is that, again, in order to have this phenomenon to happen, is this contrast between E, which has to be everywhere in space, inside and outside the source, and is conservative. So when I do the circulation, I get 0, and this one, which of course originally comes from electromagnetic interactions, but I managed to confine it in such a way that is non-conservative according to this definition here. So this confinement, this superposition of E and EM is really the beauty and the key of how a source and a current can be established in a conductor. The units we have seen, which is important again, so be careful, the units are volts, but it does not come from a conservative field, so you need to be very careful with that, to keep that in mind. And so to summarize this video, what we have done here is we introduced the concept of electromotive force. Why do we need an electromotive force? Because an electric field is not sufficient to establish a steady current. We have seen this by means of the definition of work, because I need to have, for a steady current, a closed circuit, solenoidal, and so the work would be 0 V, no work, no current. We also have seen it for the ohmic case, but this is the concept I really want you to remember. So we need a battery which generates a non-conservative force. The key is that the electric force, which of course is conservative, is defined everywhere in space, whereas this FM or EM, I managed to confine it in a confined region of space, such that the line integral over that confined region of space, which is the battery, or source, is 0, is different than 0. This different than 0 quantity, divided by Q, of course, gives me something which has units volts, and we call that the EMF, or electromotive force. And don't get confused with all this notation. We're going to use now this to understand the various cases of open, closed, and generic circuit, but I have a question for you in Piazza. So if I give you this scenario where I have here a quasi-filiform, uniformly generated wire, so uniform means with constant delta A, the question that I have for you in Piazza is, what is the question? The question is J in the conductor equal or different than J in the battery? I want you to answer that before watching, or at least think about that before watching the next video. Remember that I'm using a constant cross-section with a quasi-filiform wire, and this battery, I also assume that it's actually very small, so everything is uniform and simple. That's it.